In the Chem Activity number 10 and the corresponding videos, we will review and extend your understanding of constitutional and stereoisomers. Let us start by looking at the teaching model number 1. In teaching model number 1, you're asked to complete the charts or the columns by writing in the missing molecular formulas in both columns. Before you begin this, I'd like to remind you about some tools that you have available to you. For instance, you know that the generic formula for an alkane is CnH2n plus 2. You also know the generic formula for an alkene is CnH2n. Further, you know that a monocyclic alkane also has the formula CnH2n. So equipped with this, please consider the key question 1. So in filling in the molecular formulas for column number 1, perhaps you notice that all of the structures have 5 carbons. Therefore, they're all going to have the same molecular formula, C5H12. In column number 2, perhaps you notice that we have alkenes and monocyclic alkanes. Therefore, they all have the generic formula CnH2n, and they all have 5 carbons, so they will all have the same molecular formula. Now here we have examples in column 1 and in column 2 of constitutional isomers. All the structures in column number 1 have 5 carbons, they have 12 hydrogens, the same molecular formula, but they have different structures. They have a different attachment of atoms. Therefore, they're referred to as constitutional isomers. We also call these structural isomers. Same molecular formula, but different atom connectivity. The molecules in column number 2 also have different structures, yet they have the same molecular formula. In the key question number 2, you're asked whether that 4-carbon cyclical compound would fit best into column 1 or column number 2. Consider this now, and we'll go over it in a second. So hopefully you put it into column number 2, as it also has a molecular formula of C5H10. It is yet again a constitutional isomer of the other molecules that are in that column number 2. So this is a bit of a review of the idea of constitutional isomers. Same molecular formula, but different atom connectivity. Let's now turn our attention to the teaching model number 2. Here we introduce the molecules 1,2-dimethylcyclobutane. Before we go any further in these slides, I'd like to turn our attention to a simulation. Here we have a draw program that automatically translates the bond line drawings into a ball and stick molecular model showing the 3 dimensions. So I'd like to draw our 1,2-dimethylcyclobutane. So I make the cyclobutane. I'm going to add the wedge and dashes to represent the structures that we see in part A and in part B. So for part A, we have a methyl group coming out at us, and we have a methyl group going back. So I just need to click here again to show that. So now if we look more closely, we can see that the methyl groups are on opposite side of the rings. We've seen this situation before, and we know that this is a trans molecule. But I can also put the methyl groups on the same side. So I just click that again. And indeed, looking at the molecular model, we see the methyl groups are on the same side. The only way to interconvert between these two is to actually break the chemical bonds. There's no rotation about this ring or about any sigma bond that would allow to interconvert. But the other thing that I'd like you to notice is if we look at the carbons that have the bonds to the methyl group and to the hydrogens, in both of these structures, A and B, it's the same atoms that are attached. That is, to any one carbon, there's a hydrogen and there's a methyl group. There's a hydrogen and there's a methyl group. If I now change back to the cis, once again, I look at the carbons that are involved in making bonds to methyl groups. There's a carbon as part of the methyl group, and there's a hydrogen. There's a carbon and there's a hydrogen. So these 2 carbons that are making bonds to methyl groups, they have the same atom connectivity. And yet the molecules of cis and trans are indeed different molecules. So let's go back now to the notes. So one of the first things that we're asked to do is to label the molecules whether or not they're cis or trans. So of course the molecule on the left is the trans version of 1,2-dimethyl cyclobutane. Of course the one on the right is the cis. The next thing that you're asked to do is to look at carbon number 1 and indicate what two groups are bonded to carbon number 1 in both molecules A and B. And then look at carbon number 2 and indicate what groups are bonded for both molecules A and B. When I say group, I mean hydrogen or a methyl group, that sort of thing. So hopefully you recognize that on carbon 1 in both molecules A and B, there's a CH3 and an H. Carbon number 2, in both molecules A and B, there's a CH3 and an H. So we would say that these two structures have identical atom connectivity, and yet because of no rotation about a ring, they have a different structure. We refer to these kinds of molecules as stereoisomers. To reinforce these ideas, let's look at the next teaching model. So in the next teaching model, we summarize the two different examples. Just to run through a couple of definitions first of all, the specific atoms attached to an atom is said to be the atom connectivity, and we'd say that a pair of structures are constitutional isomers, also known as structural isomers, if they have the same molecular formula but a different atom connectivity. So that's represented by the diagram on the right-hand side. If they have a different name outside of the stereoisomerisms, and you will see that this means either whether or not it's E or Z or RS, so if they have a different name, then they have a different atom connectivity. Whereas the molecules that are on the left-hand side, well, we know that they are called 1,2-dimethyl butane, and both have the exact same name, and yet one is a cis and one is a trans. And actually that is the way that you indicate the stereoisomerism for those two. So we would say a pair of structures are stereoisomers, also known as configurational isomers, if they have the same molecular formula and the same atom connectivity, but they're not the same compound. And stereoisomers, as mentioned, cannot be interconverted by simply rotating about a bond or flipping a ring. Now, to reinforce some of these ideas, I draw your attention to the key question number 5. On the left-hand side, we have the structure 1,3-dimethylcyclopentane. We also have a number of other structures, and to kind of give it away, they all have the same molecular formula. So they're somehow related to structure number 1, and I'm asking you to consider a number of questions. So first of all, circle each stereoisomer of molecule 1. So it's always in reference to molecule number 1. And then consider, and this is in part B, well, what is the relationship between molecule 1 and the ones that you did not circle? And then finally, I'm asking you to explore molecule 5 a little bit further and draw a stereoisomer for that structure. So please pause the video and consider these questions. For question 5a, you were asked to circle each of the stereoisomers of molecule number 1. So essentially, you're exploring for all those structures that have the same atom connectivity. And actually, this is pretty simple because you're looking for those structures that have methyl groups on carbons 1 and 3. And so hopefully you circled the following structures. Considering the other structures, these are not stereoisomers for a few reasons. So for one, molecule number 3 is considered to be a structural isomer because it has a different atom connectivity compared to 1. Molecule 5 is also a structural isomer. It is 1,2-dimethylcyclopentane. Note that it has a different name than molecule number 1. And as it turns out, molecule 7 is exactly the same structure as molecule number 1. Now you were asked to explore molecule 5 a little bit further and draw a stereoisomer. One of the things you might notice about structure number 5 is that the methyl groups are trans relative to one another. So perhaps you might consider drawing the cis. So I explore this a little bit further on a different slide. So I redrew molecule number 5, and I'm now going to show you one possible stereoisomer, and that is going from the trans to the cis. Perhaps some of you, though, recognize that there's yet another stereoisomer, and that's this one. It's also an example of a trans 1,2-dimethylcyclobutane. So at first you might think, well, wait a minute, that's the exact same structure. If you look carefully, however, you'll see that in fact these are mirror images, and if you try to, for instance, flip over the second molecule to fit it on to the first molecule, it won't fit. They are non-identical. So what this does is it actually introduces the two different kinds of stereoisomers that you need to know about. The first one is called a diastereomer. And a little bit further along in this activity, I will more officially define diastereomer. The second structure is known as an enantiomer. And again, further along, we'll more officially define enantiomer. But for now, we'll indicate that these are non-identical or non-superposable mirror images. And in turn, a diastereomer is any kind of stereoisomer that's not an enantiomer.